Hi guys, welcome to part 3. See, today we are going to see how to convert a quadratic form to a canonical form by means of orthogonal reduction. See, of course, this is a very lengthy problem. This will come in 16 marks. Let's say you have to find the rank, nature, signature, as well as index. So any homogeneous equation of degree 2 in terms of 2 or more variables or any number of variables is called a quadratic form. See, here I have taken one example, that is 3x1 squared plus 5x2 squared plus 3x3 squared minus 2x2 x3 plus 2x3 x1 minus 2x1 x2. The same equation can also be expressed as 3x squared plus 5y squared plus 3z squared minus 2yz plus 2zx minus 2xy. See, if this question can be asked in any one of this form, because here the simple thing is x1 is replaced by x, x2 by y, x3 by z. Anyhow, the procedure is the same for both type of equations. See, the first thing is we have to construct the matrix corresponding to this quadratic form. See, in general, the equation 1 can be expressed as, it is the quadratic form, it is expressed as x transpose AX, where A is the matrix, which is a symmetric matrix corresponding to this quadratic form. Okay, so I can write this as x1, x2, x3. So this is nothing but the column vector x1, x2, x3. It's a transpose. So you are getting it as a row. And then I have to write the matrix, which is a symmetric matrix, then followed by that x1, x2, x3. See, now we are going to see how to arrive this matrix corresponding to this quadratic. Of course, both are the same quadratic equation. See, you have to be patient in framing this matrix. Otherwise, everything will go wrong because this is the initial step and it is a 16-mark question. Care should be taken in writing the matrix. See, as I said, it is a symmetric matrix. After completing the matrix, you can check whether it is symmetric or not, and then you can go ahead. See, now to begin with, how to write this matrix. See, we have the squared term. Either it is 3x1 squared or 3x squared, 5x2 squared or 5y squared, 3x3 squared or 3z squared. First, fill the principal diagonal elements. Say, I am writing it with the pink color, that is 3, 5 and 3, which is the coefficient of x1 squared. This is the coefficient of x2 squared and x3 squared. Or else you can say it is 3x squared plus 5y squared plus 3z squared. See, now what about these positions? I have to fill it, right? So how to fill those positions? See, actually, the coefficient of minus 2x2, x3. Suppose if I take this, that should be in the place of A23 or A32. So how to write? Half of the coefficient of x2, x3. How to remember? This is 2 and 3. So half the coefficient of x2, x3, which is nothing but minus 2. So I have to put minus 2. I repeat, in the place of A23, because why I'm going to A23 straight away means after filling this diagonal, I have the next term as 2x2, x3 or 2yz. Okay, so its coefficient is minus 2. So we have to fill the position A23 or A32 by half the coefficient of just 3, this x2, x3. Even you can have it as x3, x2, nothing wrong in it. Of course, both are the same. So half the coefficient, what is the half of its coefficient? It is minus 2. So I'll get minus 1. So I am going to put minus 1 in the place of A23 as well as in A32. So second row, third column, this is A23. So I have to write it as minus 1. Then third row, second column, so minus 1 over. Okay. Now, coming to the next term, x3, x1 means it is nothing but for A31 or A13. So how to write this? A13 is equal to A31, which is nothing but half the coefficient of x3, x1. What is x3, x1 coefficient? It is 2. So we'll get it as 1. So I can write it as 1. In what are the places? First row, third column. Where is the first row? Here, third column. It has to be replaced by 1. And third row, first column. Third row, first column means this place. So you have to replace it. You have replaced it. See now, what else we have to fill? The remaining two places are these two places. What is its position? It is the first row, second column, and this is the second row, first column element. Okay. So now I can take, see, this is A12. A12 means we have to take the coefficient of x1, x2. So A12 and A21 is nothing but half of the coefficient of x1, x2. What is the coefficient of x1, x2? It is minus 2. So I will get it as minus 1. Okay. So I'm filling this value, these two places by minus 1. So what is the matrix from this one? So what we require is the matrix A. So the matrix A is 3, minus 1, 1, minus 1, 5, minus 1, 1, minus 1, and 3. See, if you have a doubt in this construction, please take its transpose and check. 3 minus 1, 1. Yes, we have it. That is, I'm writing column as a row. Minus 1, 5 minus 1. Okay. Then 1 minus 1, 3. Yes, done. So this is a symmetric matrix. For this symmetric matrix, as we have done in our part 2, we have to find the eigenvalues and eigenvectors. So let us take this as our step 1. Okay. So our step 1 is this. So I'm highlighting it. So this is our step 1. So in our step 2, we are going to find the eigenvector. So how to find the eigenvectors? Eigenvectors, you know, in the part 2 I have explained in detail. You have to find the determinant of A minus lambda I equal to 0. Solve it, which is nothing but the characteristic equation, or else you can write it as lambda cube minus S1 lambda squared plus S2 lambda minus S3 equal to 0. See, in this, you know that these are the principal diagonal elements 3, 5, 3. So S1 is nothing but the sum of the principal diagonal elements, that is 3 plus 5 plus 3, and S2 is nothing but the minus of the principal diagonal element. For example, if I take the first term 3, its minor is nothing but 5 minus 1 minus 1 3. It is a 2 by 2 determinant. So similarly, I have to find for 5 and for 3. Then find your S2, put it in its place. S3 is nothing but your determinant value of A. So we get what are the values now? We have got S1 as 11. So S2 is nothing but the sum of the minors of the principal diagonal elements, the 36, and S3 is also 36. Okay. Therefore, how we are going to write the characteristic equation? This is our equation number 1. So the characteristic equation 1 is given by lambda cube minus 11 lambda squared plus 36 lambda minus 36 equal to 0, because minus S1 means minus 11, S2 lambda, that is 36 lambda, minus S3, so I have it as minus 36 equal to 0. Now we have to solve this equation in order to find the eigenvalues. So this, you know this is the characteristic equation. Any clarification you can verify part 2. So on solving this, first you use synthetic division method, and then finally you come to the quadratic equation solution method, and in that you will be getting the values as eigenvalues as, what are the eigenvalues we'll get? Eigenvalues means on solving this, we are getting it as 2, 3, and 6. Next step is to find the eigenvector, namely x, and it is given by A minus lambda I of x is equal to 0, and it is the matrix A in which the diagonal elements we had to put a minus lambda, so 3 minus lambda, 5 minus lambda, 3 minus lambda. Rest other elements will remain the same, and we have for x it is x1, x2, x3 equal to 0. Now for one case I have explained, for lambda equal to 2. If you want it to be in more details, you can verify my part 2. So here lambda equal to 2 means it is 3 minus 2, 5 minus 2, 3 minus 2, and rest of the elements will remain the same. And from this we'll be getting equations like 3 minus 2 is 1, so 1x1, and minus x2 plus x3 equal to 0, minus x1 plus 3x2 minus x3 equal to 0, x1 minus x2 plus x3 equal to 0. On solving these equations, a homogeneous equation, apply the rule of cross multiplication, and in that we will be getting the value of x as 1, 0, minus 1. Okay. See now for lambda equal to 2, we got the eigenvector as 1, 0, minus 1. And for lambda equal to 3, we get the vector as 1, 1, 1. And for lambda equal to 6, we get the vector as x is equal to 1 minus 2, 1. Again, I repeat, for more clarification, you can refer part 2. See, now we'll go to the next step, step 4. That is, in this, we are going to find the modal matrix. The modal matrix is nothing but the eigenvector matrix, which is given by 1, 0, minus 1, 1, 1, and 1, minus 2, 1. So from this, we have to construct the normalized modal matrix. Normalized modal matrix is nothing but 1 divided by the square root of sum of the squares of the sum of the squares of the elements in each of the column, that is 1 squared, 0 squared plus minus 1 squared. Then 0 divided by the same procedure, sum of the squares of the elements in each column, that is 1 squared plus 0 squared plus minus 1 squared. So I'll be getting it as 2, and this as 1 divided by root 2. And coming to the next term, it is 1 divided by the sum of the squares of the elements in that particular column means 1 squared plus 1 squared plus 1 squared. So it is 3, and this is 1 by 3, and again it is 1 by 3, and here I'll get 1 divided by the square root of 1 squared plus minus 2 the whole square plus 1 squared. So it is 1 plus 4 plus 1. So I'll get it as 6 minus 2 by root 6 and 1 by root 6. So this is what we call as the normalized modal matrix. So before constructing the normalized modal matrix, it's the most important one is verifying the vectors, whether the vectors are pairwise orthogonal or not. So pairwise orthogonality condition is nothing but x1 transpose dot x2 equal to x2 transpose dot x3 equal to x3 transpose dot x1 equal to 0. This is a very, very important condition that we have to verify before normalizing it. So x1 transpose means it is nothing but the transpose of this column matrix. So which is x1 transpose dot x2, that is 1, 0, minus 1 into x2. x2 is nothing but 1, 1, 1. For clarification, let me take this as 2, this is 3, and this is x1. Okay. So this is equal to 1 into 1, 0 into 1, minus 1 into 1. So I'm getting it as 0. Then if I take the next one, that is x2 transpose dot x3. x2 transpose is nothing but 1, 1, 1. And with that, we are multiplying 1 minus 2, 1. And we'll get it as 1 minus 2 plus 1. Again, it is 0. And x3 transpose dot x1 is equal to 1 minus 2, 1. And our x1 is 1, 0, minus 1. So I'll get it as 1, 0, minus 1, 0. Therefore, we conclude that the vectors, the eigenvectors are pairwise orthogonal. So this is a very important step that we have to verify, and is true for any symmetric matrix. Transpose. N transpose is nothing but the transpose of the given matrix N. That is the matrix just we have found. So we have to take the transpose, that is write the column as row and row as column. That's I'll get it as N transpose as 1 by root 2, 0, minus 1 by root 2, 1 by root 3, then I have 1 by root 3, then 1 by root 3, 1 by root 6, and then minus 2 by root 6, and 1 by root 6. So now we have got the matrix N as well as N transpose. The next step is, that's our sixth step. So in this, what we are going to do is we are going to diagonalize the matrix A. So this is the procedure you have to follow for any of the matrix to be diagonalized. So diagonalization D is nothing but N transpose AN, and the procedure what we follow is orthogonal transformation. Okay, it is called the orthogonal transformation. So we are going to make the matrix, or we are going to convert the matrix A to a diagonal matrix. So N transpose, we know that it is 1 root 2 0 minus 1 by root 2, 1 by root 3, 1 by root 3, 1 by root 3. Then I got 1 by root 6 minus 2 by root 6, then 1 by root 6. With this, we are going to multiply the matrix A. The matrix A is nothing but, you know that, it is 3 minus 1, 1, then minus 1, 5, minus 1, then you have 1, minus 1, and 3. And this is N transpose, this is A, and now I'm going to multiply with this N. So N is what? 1 by root 2, 1 by root 3, 1 by root 6, 0, 1 by root 3, 1 minus 2 by root 6, and then we have minus 1 by root 2, 1 by root 3, then I have 1 by root 6. Okay. See, we can use calculator. Any of the scientific calculator is allowed in the examination. So you can use this easily to find the product of the three matrices, or else you do it manually. You know the matrix multiplication. On multiplying these three matrices, you have to get a diagonal matrix in which the diagonal elements are nothing but the eigenvalues. So what are the eigenvalues we got? We got it as 2, 3 and 6. So after multiplying these three matrices, we'll be getting like this. So you'll be getting that 3 eigenvalues in the diagonal. That's very important. Even if you go wrong, you can check it. So when you multiply the three matrices, this is the diagonalized matrix. So this is nothing but the 2, 3, 6 are called the spectrum of the matrix. So we got the eigenvalues in that diagonal. So we have diagonalized this matrix A to a matrix with 2, 3, 6 as the eigenvalues. See, now after this, we have to go to step 7. So in this, what we are going to do is we are going to take a linear transformation x is equal to ny such that our quadratic form, how it is expressed, it is x transpose ax. So you go to the first step of our problem. There we have expressed the quadratic form x transpose ax. See, now, right now, up to this step, you have diagonalized. Now we have to convert the quadratic to a canonical form. So for that, we are using this linear transformation x is equal to ny. So this quadratic form, x transpose means it is ny the whole transpose a and ny. So now when you take the transpose of the two matrices which are in product, you will get y transpose n transpose a n y. See, now you know that n transpose a n is nothing but equal to our diagonal matrix D. We got it from the previous step. So it is y transpose dy. Y transpose means it is nothing but y1, y2, y3, and D is the matrix we got just now. It is 2, 0, 0, 3, 0 and 0, 0, 6. With that, you have to multiply the column matrix. It is y1, y2, y3. See, now you have to multiply these three matrices. You know, this is a matrix of order 1 by 3. This is a matrix of order 3 by 3. When you multiply these three, you will get a matrix of order 1 by 3. And that's again multiply with the matrix of order 3 by 1. So you'll be getting a 1 by 1 matrix finally. So now you will get this equal to 2y1 squared plus 3y2 squared plus 6y3 squared. Okay, to be more precise, these are nothing but the eigenvalues which got initially from your step 1. So it is 2 into y1 squared plus 3 into y2 squared plus 6 into y3 squared. By closing your eyes, you can say that immediately after getting your eigenvalues, you can put all the three eigenvalues with the proper sign, and you can conclude it is 2y1 squared plus 3y2 squared plus 6y3 squared. So this has to be the answer for the problem. See, now with this, we have converted a quadratic to a canonical form. This is what we call the canonical form, and we call it as a CF. And what procedure we have adopted is nothing but the orthogonal transformation. So see, now we have come to the end, almost to the end. Now we are yet to find the rank, signature and nature of the quadratic form. So now rank is nothing but the number of eigenvalues, non-zero eigenvalues. I repeat, rank is nothing but the number of non-zero eigenvalues. How many values we got here? There are 3 values, that is 2, 3, 6 namely. Then we have index. Index is nothing but, index normally we denote it by P, and P is nothing but the number of positive terms or positive eigenvalues. Positive terms in the canonical form, they say other way. So number of positive terms or positive eigenvalues is nothing but, again we have it as 3. Okay, so the number of positive term is nothing but equal to 3. And now we have signature. Signature is nothing but equal to, it is defined as yes, which is 2p minus r. And you know, p is nothing but 3 and r is also 3. So you will have 6 minus 3, which is 3. Okay. Now finally we have come to the nature of the quadratic form. So the nature is nothing but for this particular problem, it is positive definite. So we call it as positive definite. So to more about this nature, I'm giving you a note. Please make a note. Please have it in your mind. If all eigenvalues are positive, okay, eigenvalues are positive, then we call it as the nature is positive definite. Okay, it is called a positive definite. Okay. If all eigenvalues are negative, we call it as, then the nature is negative definite. Okay, this is called a negative definite. If some of them, some positive and some are negative, okay, then the nature of the quadratic form is indefinite. Okay, it is called indefinite. There are 2 more cases. At least one eigenvalue is zero, and the rest are positive. Rest others are positive. Then the nature is called positive semi-definite. What is it called? It is called a positive semi-definite. At least, the next case, at least one eigenvalue is 0 and the rest others are negative. Okay, negative. Then we call it as negative semi-definite. Okay, so altogether we have 5 cases. Please keep it in mind when you are going to find the nature of a given quadratic form. You have to keep all these things in mind. And with this, I'm completing this part. And if you have any doubt, you can you can raise your question in the comment box. And in the next video, I'll be dealing with the Cayley-Hamilton theorem. Thank you.